once again to my channel. Today we are going to do organic chemistry, and it's mainly about the stereochemistry, chirality, and also chair conformers of cyclohexane compounds. Okay, so when we are talking about cyclohexane, this is the normal structure for cyclohexane. Okay, this is the normal structure for cyclohexane, but when you are writing it in a chair conformer, this is how you write the chair conformer of cyclohexane. So let the basis be your stand. You have to know this thing before we can proceed with all what you are coming to do for the day. Okay, so this video will be divided into two. The first part will be explaining chirality and all those stuff, while the other part will be explaining the both conformers and how to determine the stability of an organic compound using the chair conformer. Okay, so to begin with, let's talk about bicyclo compounds. When we are talking about bicyclo compounds, they are actually compounds. They are actually cycloalkanes. Okay, they are cyclic compounds. But here, these cyclic compounds have been what? Attached. Okay, it's like they have been fused together, and we are having those two compounds as one. Okay, so let's take this compound for instance, which is what? Disilene. The common name for this structure is disilene. But when we are talking about naming this compound in terms of IUPAC, it is called bicyclo. Okay, the bicyclo is always there. This is that there are two cyclic compounds that have been fused. 4,4,0 decane. Because you see, when you take the structure, you can come from here 1, 2, 3, 4. You can take any direction. 1, 2, 3, 4, 5, 6, 7, 8. At the end, it's going to give you 10. Okay, 1, 2. You can see the numbering. Here, you see the line between this one and this one. There is no methyl group, or there is no carbon in between these two groups. So for that matter, here is 0. Okay, this place is 0 because there is no carbon compound between these two, or between the first carbon and the sixth carbon. There is no other compound. As time goes on, you will understand why this compound will be having a different name as compared to this. Okay, so when we are talking about this one, the reason why we are not having any carbon compound between these two compounds, that is why it is 0. Okay, so this represents the 0. This is the middle one. And when we are talking about the 4, you could see that when you are neglecting these two, boundaries, okay, the number of carbon atoms that are located on each side will also give you these two numbers. So when you are taking our left, this is 1 carbon, 2 carbon, 3 carbon, 4 carbon. So there are 4 groups of carbon on the left, and on the right, 1, 2, 3, 4. There are also 4 carbon groups on the right. So here we are having 4, 4. Then there is no atom here, so 0. So bicyclo, 4, 4, 0. Then decane. It is decane because after all, it is having what? 10 carbons. When you number the system, when you number the bicyclic compound, it is having what? 10 carbons in all. Reject all. When you ignore the boundary here, and you have to ignore the boundary and number it cyclic. You are going to consider this bicyclo compound as 1 and name it like how you name the cycloalkane compound. So you are going to, so here it's having 10 carbons in all. That is why it is called decane. Okay, so let's move to the next. When we are talking about, let's take this compound for instance. Let's take the example 2 for instance. If you can see the example 2 very well, here there is no boundary between the 5 and the 1 carbon, so it is 0. You see what I'm getting? So here the 0 is there, but when we take the right side, we are having only 3 groups of carbon on the right, which is 1, 2, 3. And when we take the left, we are having 4 carbon groups. So now you could see 3, 4, 0, no name. Bicyclo. You should always indicate the bicyclo because it is 2 cyclic compounds that has been fused to give 1. So it is what? Bicyclo, 3, 4, 0, no name. Okay. Then let's go to the third example where we are going to get this thing very clear. When we are taking the third example, you could see this very compound that this compound has been fused. Okay. You could see very well that it has been fused from here 1, 2, 3, 4, 5, 6. Okay. And another one has been fused 1, 2, 3, 4, 5. Then from here, there's a projection indicating that there is what? A carbon atom, which is the 10. There's a carbon atom in between these two. So for that one, when you are naming your compound, it won't be 0. It will rather be 1 because there's a group of carbon atom, or there's a carbon atom in between the boundary. Okay, so on the right we are having, I think, 3 carbons. So 1, 2, 3. On the left on the right we are having 1, 2, 3, 4. On the left we are having 1, 2, 3, and there's a 1 in between it. So bicyclo 441 decane, because after naming all the organic compounds, we are going to get what? 10. Or after numbering the organic compound, we are going to get 10 carbons in the system. Always note that we are going to ignore the boundaries between them. So we are going to get 10 carbon compounds, which is actually what? A decane. So bicyclo 441 decane. Okay. Now, I hope this part is very clear. So when you go, you can try some of the examples, or I'll be posting some of the examples in my bio. You can go and check it out and also give the names. Later, I'll be doing a video about it, explaining how the names came by. Okay, so now let's move to the ways to create isomers. There's an easy way to create isomers from a compound. Let's say they will give you pentane. No matter the structure that they will give you, you can just what? You can just form isomers from it. Specifically, alkane compounds. When you're given alkane like pentane, okay, this thing is the parent structure, but you can break it into fragments. We are having 1, 2, 3, 4, 5. You can break this part, okay, and put it at everywhere on the structure. When you put it at everywhere on the structure, it's going to give you what? A different compound, which is having the same molecular formula, but what? Different structure. So here, I break this part and I place it here. And now I'm having what? 2-methyl-butane. You see how it is? Very easy. Here too, you can also break this part, So now you're having what? 2 fragments. You can locate one here, you can locate one here, giving you something like an X. Ignore this one because I'm just showing that this place has been broken. Just a fragment has been broken and it has been attached to the part of it. So here you see 1, 2, 3, or 1, 2, 3, or 1, 2, 3. They are all the same. But on the second carbon, there are 2 groups, which is what? 2 methyl groups. So now we are having what? 2,2-dimethyl propane. You see how it is? At the end, that 2,2-dimethyl propane is having what? The same molecular structure, the same molecular formula as pentane, but the structure is not the same. Let's move to hexane. With hexane, I think you get it better. So let's move to hexane. So, with hexane, see the hexane structure. Okay, you can break this part. You just break this part. Put it anywhere you like on the carbon, but make sure that you are not going to put it at the terminal. If you put it at the terminal, you are still going to get hexane. Okay, so you can break this part and put it here, or put it here, or put it here, anything else. So with the first one, I'm actually not having space, so I'm just going to give you 2 isomers in one. Here, you're going to break one, put it here, you are getting what? 2-methyl what? Pentane. You can also put the methyl group in between, which will give you what? So you can remove this methyl group, put it here, which will give you 3-methyl pentane. I hope you get what I'm trying to say. If you are not getting what I'm trying to say, you can pause the video and try your hands and see whether you are getting what I'm trying to say. In the same or in a similar way, you can also what? Break 2 parts of it. You can break this part, you can break this part. Now you're having 2 fragments of methyl group. You can put one of the methyl group here, you can put the other methyl group here, giving you what? 2,3-dimethyl-butane. So that's one of the easiest way. That's one of the easiest way to what? To form isomers when you are given a compound. Okay. Now let's move to Newman projection. When you're talking about Newman projection, it's just a way of what? Drawing organic compounds in 3D, viewing from specific angles of the carbon in the organic compound. Okay, so now let's get to this part. You see, we are having propane. You see, this is the structure for propane. You can also write it in the normal condensed form or open structure. This is the formula for butane. So any dot that you see is just what? Hydrogen. I'm just representing the dot as hydrogen to save time. Now, so when you are viewing the propane from the first and second carbon, you will take your first carbon. This is your first carbon. Okay, this first carbon, this is your carbon. That first carbon here, you can see, has been divided, or it is bonded to what? 3 hydrogens, and the other bond is bonded to carbon. So that one we are not going to show it. Keep it in mind. That's all about Newman projection. If you are able to get this strategy correct, then that's all. Note, this is it. This is your first carbon. your first carbon is bonded to 3 hydrogens, 1, 2, 3. It is bonded 1, 2, 3. There's nothing you are going to do about this. Okay, so ignore this one. Now they are saying that from the first and second carbon, you have to come to the second carbon. Now when you come to the second carbon, we don't draw the same structure. We rather represent it as what? A circle with this what? With these dashed lines. Okay, so carbon can form maximum of 4 bonds. So this is that already it is having 1 bond left. This one too that you've made is also having 1 bond left. So these bonds are going to what? Join carbon-carbon to form this bond that I'm trying to say. So do not focus on this one. Just focus on what? The hydrogens that this carbon has been bonded to. Now when you come to the second carbon, this is the second carbon. Okay, this second carbon has been bonded to what? 1 hydrogen here and 1 hydrogen. But look at the other side. The other side is not bonded to what? Hydrogen, but it is bonded to what? C, or another carbon with what? 3 hydrogens. And this group, you have to consider this group as a substituent. That's the best way I can explain to you. You have to consider this group as a substituent. Okay, when you consider this group as a substituent, you are going to get something like CH3, which is a methyl group. Okay, so now you are having your H, you are having your H, you are having your CH3. So from there, you impose this one on this. You are going to impose this structure on this structure to get something like this. So you can write it anyhow, just draw it. But the best way or the preferable way is what? Draw the circle with the H atoms and CH3. Then you come and impose this structure on this, which is what? Hope you can see what I'm doing. So now you are having H, then you have your CH3 at the bottom. So now, after you've gotten the structure, we can get it in different orientations. And this one is the staggered conformer or the staggered conformation. This is where the atoms are directly opposite to each other. So you can see this hydrogen directly opposite to the methyl group. This is directly opposite to this. This is directly opposite to this. This is the staggered conformer. Now let's take a look at the eclipse conformer. We are having something like eclipse conformer, and this is where you are having this structure. Also, you have to rotate this one. When you rotate this one, the CH3 will come here, H will come here, H will come here. Okay, then you superimpose it on this structure. You are going to get something like this. Okay, but because of your writings, you have to. So at the end, for the eclipse, you have to keep it in mind that the atoms that you are viewing from. The atoms that you are viewing from will be overlapping with the one behind. So you're not going to see any atom. In reality, you're not going to see the atoms behind it, though they are atoms. But when you are drawing it or when you are writing it, you have to always make sure that you indicate that it is an eclipse conformer by just drawing the lines slightly close to the other lines to show that it is an eclipse conformer. And the angle between this is 180 degrees. But the angle between the groups of atoms in the eclipse is 0. For that matter, when they give you any qualitative question like staggered conformation and eclipse conformation, which one is more stable, is staggered conformation. Why? This is because the atoms are not closer to each other. For that matter, the torsion strain, when I'm talking about torsion strain, it's all about repulsion or something. Okay, so there will be less repulsion as compared to this eclipse conformation, where the atoms are directly overlapping with the other. And if they are overlapping, what happens? They are close to each other. For that matter, there will be repulsion. So let's say if you are having a compound to be formed with a mixture of a staggered conformer and an eclipse conformer, it will be very, 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 very possible that about 99.9% of the staggered conformer molecules will be formed as compared to the eclipse conformer. Okay, so now let's move. Now, let's move to something more further. So now, let's consider pentane. Okay, to improve your understanding, let's consider pentane. And for this pentane, we are actually looking at it from From the second and third carbon. Okay, so this is your pentane structure. Sometimes they will give it to you as a dash form. If you want to do it well without any confusion, just write it this way. With your hydrogens, then they say from the second carbon and third carbon. So you can take your second carbon from here and third carbon from here, or second and third. Anything will give you the same answer, or it will arrive in the same answer. Now, you take your second carbon. When you take your second carbon is bonded. I always tell you that the moment you take the second carbon or you take the specific carbon, just ignore the bond with the other carbon atom. Ignore it and consider only this. Okay, if you consider only this carbon is bonded to what? Hydrogen. But how about this side? This side has been bonded to what? A methyl group, which is CH3. Okay, so now you're having something like H, then CH3. This CH3 can come here, this CH3 can come here. You can just interchange them. They are going to give you the same thing. Now, when you take this one, for instance, from the third carbon, this is your third carbon. You have to also ignore the bond that exists between the two carbons. You have to ignore it and only consider this part. So when you consider this part, okay, this carbon is bonded to what? Hydrogen, and the other one is what? Two carbons, each with what? Hydrogen. So here, if you are very observant, you can see that what? There are two carbons with what? How many hydrogens? 5. 1, 2, 3, 4, 5. Okay, so here, instead of it being what? CH3, C3H7, it's rather supposed to be what? C2H5, as you can see. Okay, if you are very observant, you could see that what? From here, the group that has been bonded to what? This carbon atom is just what? An ethyl group, which is C2H5. Okay, so now you have to impose this structure on this to get the Newman projection. And it's very easy. After you've gotten this, if you're able to get these two correct, that's all. You are just moving. So now, looking at the staggered conformation. Look at the staggered conformation. This is the staggered conformation, where you impose the other one. So this one is supposed to be what? C2H5, not C3H7. It's not a propyl group, but it's rather an ethyl group. So here, you are going to impose the other structure on this, and you are going to get your CH3 here, HH. I told you that you can interchange the methyl group. So you're having your CH3 here, you're having your H, and you're having your H. And the other group, the other structure that you imposed on, it's also what? H, then what? C2H5. So the same thing also applies. When you are considering the eclipse conformation, I told you that the eclipse conformation, in reality, this CH3, this C2H5 is directly on the what? On this CH3. For that one, it is what? Overlapping with it. So you are not going to see it. But when you are drawing it, you have to show that because it is eclipse, when you are drawing it, you have to just draw the line slightly from these two to show that it is eclipse. The angle between these two is what? 0. For that matter, it is never what? Stable. There will be increase in torsion strain. For that matter, it's going to what? Repel each other. The groups of atoms in the molecule is going to what? Repel and making it what? Unstable. So hope you can try more questions. I'll be posting more questions in my bio, so be always attentive, and when you get a notification, just try and check it out, solve more questions on it, and it's going to improve your understanding about Newman projection. In case you don't understand anything too, you can just send it through the comments. I will see it and I'll reply you, or I'll do a video to reply it. Now let's go to the foundation towards chirality. When I'm talking about chirality, it's just a molecule. Chirality or chiral centers in organic chemistry is all about a compound, specifically carbon. Okay, it's not any compound or it's not any group of atoms. It's specifically carbon, and this carbon is bonded towards 4 different groups. It's bonded to 4 different groups of atoms. Okay, for instance, let's take the examples that have been provided here. For instance, you see this carbon, it is bonded towards hydrogen. OH group, which is a hydroxy group, chlorine, which is an halogen, and this one is an alkyl group, methyl. When you consider all the atoms, there is no atom that is similar to the other. All of them are different. For that matter, this carbon or this center is called what? A chiral center. And it's a chiral center because when you create a mirror image of these two, now you can decide to draw it in a 3D form using a dash wedge presentation. You can use this dash wedge presentation to draw this compound in a 3D form. That will make you understand it very well. Now, as you are seeing something like this is a mirror. You are having your compound here. You put a mirror this short dash means that what this CH3 is behind the plane, this wedge, okay, which is a Cl. So here is supposed to be what? Cl, Cl. Okay, this means that what? This one is outside the plane, and these two are in the plane, are in the same plane with what? Carbon. So now when you use a mirror, to get a mirror image of this thing, now when you take this carbon or when you take this molecule and you impose it, it will never be possible. Okay, it's never. That's why they are said that what they are what super non-imposable, or they are superimposable of what of each other. Okay, though they are forming a mirror image, when you try to what impose this molecule on this, you are never going to get it to be what to be imposed, or they will never fit. That's the right way. They will never fit when you try to impose. Yeah, they will never fit. You get your Cl to be somewhere here and your OH to be somewhere here. You are never going to get what the structure fitting into the other. So for that matter, they are not what superimposable. Let's move on. So now let's consider 2-methyl-butane. When you take 2-methyl-butane, this is the structure. This is butane. Apparent structure is butane. We are having an alkyl group which is methyl, so CH3. All the other carbons are bonded to hydrogen, but I just don't want to show it because after all we know advanced form of it, or advanced form of writing it when you want to save time. So everything is bonded to hydrogen. Now, if you are asked to check whether the compound has a chiral center, what are you going to do? You take the first carbon. When you take so one thing you have to get in mind that you have to know the meaning of what chiral center. And the chiral center, as I explained earlier, means what? The compound is bonded to what? 4 different groups. Okay. So here, when you take the first carbon, this is the first carbon. The first carbon is bonded to what? Hydrogen, hydrogen, hydrogen. So at that instant, you can even conclude that this thing is not a chiral center, because already there are 3 similar groups that is bonded to this carbon atom. So that one out. If you want to save time, there's no need to go further. The moment you realize that there are 2 similar groups of atom that is bonded to the center, out, it is achiral. Now, when you come to the second carbon, look at the second carbon. This second carbon is bonded to what? CH3, which is the 2 methyl. So the methyl group is here. This same carbon is bonded to another methyl group. So the moment you are able to realize this, out, regardless. But listen well, in case you are having this one to be chlorine or chloro, hydrogen, methyl group, and this one is ethyl group, they are never the same. So it's what? A chiral center. Ethyl group is different from methyl group. So assuming there is a Cl atom here, or there's a Cl group here, or halogen, or any other group of compound different from this is a chiral center, because methyl group is different from ethyl group. So they are 2 different things. Don't be assuming that because there's a carbon here and there's a carbon here, for that matter, it is not a chiral center. Okay, so now let's go to the third carbon. When we come to the third carbon, this is it. This is the structure. This one is different from this. Okay, but at the end, there are 2 hydrogen atoms that have been bonded to the carbon. For that matter, we are not going to consider it as what? As a chiral center. Okay, so if you move on further, you will notice that what? The compound does not have what? A chiral center. So a compound like 2-methyl-butane does not have what? A chiral center. Okay, so now let's move to more interesting questions. Okay, so now let's consider 2-chlorobutanol. This is a different compound, 2-chlorobutanol. It's a compound that you can draw using the name, and this is what? This is a butanol with the OH group in the parent structure. Remember, we always give priority to the hydroxy group or the alcohol group. Here, this one is your substituent. 1, 2, 3, 4. 2-chloro. I hope the naming is more important. So if you're able to draw the structure, then you'll be able to what? Identify whether there is a chiral center or there is no chiral center. So if for this compound, if we are asked to determine whether there is a chiral center or not, when we take the first carbon, see the first carbon. This is the first carbon. You can actually indicate that what there's what 2 hydrogen atoms here, which is similar. So away, it's not chiral. When you take the second carbon, see, there's an ethyl group here, and there's what an alcohol group. There's a chlorine group, which is halogen, and there's what hydrogen atom here. All the atoms that are bonded to the what to the center is what completely different. For that matter, you are going to consider this as what as a chiral center. Okay, a molecule or an organic compound does not have only one what. If it is a chiral compound, it doesn't mean that it should only have what one chiral center. The compound can have more than one chiral center. So it's all about you just going systematically like how we did. Just go systematically, and you are going to get what there are most of the compounds that you are going to get more than 2 chiral centers. Some are 3, some are 4, depending on the structure that they will give you. So just go systematically towards what we've gone, or how. See the steps. Okay, you just go through the same step, and you are going to what you'll be able to what, or you'll be perfect in determining whether there's a chiral center or there's no chiral center. So this is an example that you can pause the video and try it. It's very important. You can just try your hands on it to test your understanding. Okay. So now, let's move to the stability of what compounds, or stability of organic compounds per se, especially when you are replacing some groups of what atoms in an organic compound. Okay. Here, I urge you that you actually pay attention to what I'm going to discuss here, because it's very important. Because when we are talking about primary hydrogens, secondary hydrogens, and tertiary hydrogens, they are something very simple. But if you don't know this basis, it will be very difficult for you to understand this concept, the concept that you are going to go by. So when we are talking about primary hydrogens are actually the hydrogens that are bonded to carbon. They are hydrogens that are bonded to a carbon atom, and this carbon atom is bonded to what? Another one carbon atom. Okay, that's all about primary hydrogens. And when we are talking about secondary hydrogens, the hydrogen is bonded to a carbon, and that carbon that the hydrogen has been bonded to, that carbon is also bonded to what? To 2 other carbon atoms. Okay. So when you look at this, for instance, when you look at this CH3, this carbon is bonded to what? Only one carbon here. Okay, so all these hydrogens are what? All these 3 hydrogens here are primary hydrogens. The same thing applies here, primary hydrogen. Okay, so now in this compound, there are what? 9 primary hydrogen in the compound or in the molecule. When we are talking about second hydrogen or secondary hydrogen. Secondary hydrogens, as you can see, the secondary hydrogens, there is no secondary hydrogen here because there is no carbon atom that has been bonded to other 2 carbon atoms. So there is no secondary hydrogen. But look at the tertiary hydrogen, for instance. This one is a tertiary hydrogen. Why? Because it has been bonded to a carbon that is also bonded to what? Other 3 carbons. Okay, so as you can see, this carbon is bonded to what? 1 carbon and 1 carbon, 1 carbon. So this hydrogen is what? A tertiary what? Hydrogen. Okay, don't forget to subscribe and like it. You can comment when you don't understand anything. I will see it and I'll reply you, either with a video or with a test. Okay, so now let's look at example 2. This compound is the same thing as this. Okay, so sometimes they will give you the structure in this way. If you want to understand it better and know the number of, let's say, primary, secondary, or tertiary hydrogens, you just have to draw the plane structure, or you just have to write the plane structure. That will also help you to determine the number of primary, secondary, or tertiary hydrogens. So you can see from here, this carbon is bonded to what? Only 1 carbon. For that matter, all the hydrogens that have been bonded are what? Primary. But this one, you see, this carbon has been bonded to 1 carbon here, and also bonded to another carbon here. So these 2 hydrogens here are what? Secondary. For that matter, in this molecule, there are what? 2 secondary hydrogens. There is only 1 tertiary hydrogen, and there are 9 primary hydrogens, as you can see. So in the synthesis of alkene compounds, especially in chlorination, they will give you some ratio, a ratio like hydrogen with a degree. This means that this is a tertiary hydrogen, this is a secondary hydrogen, this is a primary hydrogen, and it is corresponding to a specific rate or a specific number. The third hydrogen, or the tertiary hydrogen, is corresponding to 5. The second hydrogen is corresponding to 3.8, and the primary hydrogen is corresponding to 1. Okay, so this actually shows how fast a tertiary, a primary, or a secondary hydrogen will be replaced by a chlorine atom in the process of chlorination. Okay, so now let's move to an example. This example will help you get everything right. So now, when we are taking an example when we are using chlorination, for instance, you see, so when we are having chlorination, we are also having bromination. We are having iodization, or see, so it's all about the halogenation reaction, and each has a rate. So using 2-methyl-pentane, for instance, here we are having our 2-methyl-pentane. 2-methyl, there's a methyl group on the second carbon and pentane. Okay, so here you have to determine the number of primary hydrogens. Primary hydrogens 3, 6, and 9. Okay, so there are 9 primary hydrogens. The secondary hydrogens are 4, 1 and 2. I've already explained to you why these 2 hydrogens are these hydrogens are primary, because they have been bonded to a carbon atom, which has been bonded to 2 other carbon atoms. So now, and our tertiary hydrogen is 1. We are having only 1 tertiary hydrogen, which is this one. Okay, so for now, let's move here. Okay, let me remove this thing because this is just a reminder. I'll later let you know what's about. So now, here, you see the primary hydrogen, the range that I gave you. This is the range: tertiary hydrogen, secondary hydrogen, and primary hydrogen. So there are 9 primary hydrogens. So the 9 times the rate, so 9 times 1. Okay, which will give you 9. Okay, then the secondary hydrogen is 4. There are 4 secondary hydrogens. So the number of the secondary hydrogens times its rate, which is 3.8. Okay, then the primary, which is then the tertiary, which is having a corresponding rate of 5, is 1 times 5. You see how it is. So now we are having 9, 15.2, and 5. Okay, so if you want to know the amount of a specific compound that has been formed, okay, by, let's say, a replacement of primary hydrogen, you just take the value of the primary hydrogen, which is your 9, divided by the sum of all the 3, 9 plus 15.2 plus 5, times your 100 will give you the percentage of the compound that has been formed when you replace a primary hydrogen. Okay. The same thing also applies to secondary hydrogen, or the secondary compound. The secondary compound is actually the compound that has been formed when you replace a secondary hydrogen. So here, for the secondary hydrogen, we are having the rate to be 5. Okay, the secondary hydrogen, you are having the rate to be no, this one is the tertiary hydrogen. So here today, I think there's a mistake that you should also correct here. This one is rather supposed to be a tertiary, and this one is rather supposed to be a secondary. Okay, I was quite in a hurry, so forgive me about that. So here, this one, okay, you let me change it so that you don't get confused here. Okay, so hope you are all good. Don't mind my handwriting. So tertiary, so this is a tertiary. So if you want to know the amount of compound that has been formed when you replace the tertiary hydrogen, this is 5 divided by the sum times 100. This is going to give you 17.123%. And when you take the secondary, this is a secondary, which is 15.2 divided by the sum times 100. So at the end, make sure that when you add all these two, When you add all these three, you should get 100. If you don't get 100, know that you are dead and gone. You should get 100 because it's just a percent. It's a percentage that you are expressing. So after adding everything, you should get 100. Okay. So now, let's move. So here they said note, primary compound. So the primary compound that will be formed, the primary compound that will be formed could be what? Two or more what? Different primary compound. Because here you are replacing what? You are replacing primary compounds, or you are replacing primary hydrogens. Sorry, you are replacing primary hydrogens. So if you are replacing primary hydrogens, here there's a primary hydrogen here, there's a primary hydrogen here, there's a primary hydrogen. You see, so for that matter, the chlorine can replace the hydrogen here, giving you something different. The chlorine can also replace the hydrogen here to give you something also different. If the chlorine is here, you are going to get something like what? Here, you are going to get something like 1 chloro, then let's say 4 methyl pentane, or 1, 2, 3, 4, 5. So 1 chloro, 4 methyl pentane. Assuming the chlorine is replaced here, you are going to get what? You are going to get chloro 2 methyl, because you are going to consider your longest continuous chain to be this way. So chloro 2 methyl pentane. So there are two different compounds. The moment the position of the chlorine atoms has been changed, there are two different compounds that have been formed. But for the tertiary compound, it's only one thing that will be formed. For tertiary, in this example, for tertiary, you should keep in mind only one compound will be formed, because there is only one tertiary hydrogen that was there, entirely replaced by the chlorine. So for the tertiary compound, only one thing will be formed. And what do you think the name will be? The name will be what? 2-chloro 2-methyl, then pentane. You see, 2-chloro 2-methyl pentane. That's the name. Then for the secondary, you see the secondary, there are two secondary spots here. There is a secondary hydrogen here, there's a secondary hydrogen here. So the chlorine can replace it to give you what? 3-chloro, or let's say 2-methyl 3-chloro pentane. Okay. Or the chlorine can replace this one to give you what? Or the chlorine can replace the hydrogen here, the secondary hydrogen here, to give you what? 2-chloro 4-methyl pentane. You see? So now this is just a reminder that I want you to know. This is a reminder that from the examples that have been solved, how many different compounds can be formed from the primary. So that's what we have discussed earlier. Okay, so they can ask you that how many different compounds can be formed in, let's say, the secondary compound. They can ask you how many different compounds can be formed. The tertiary, so they can ask you how many different, but for this one, for the tertiary, you should know that for the tertiary, it is strictly what? Only one compound be formed, because there is what? Only one tertiary hydrogen. Okay. Then there's one thing I also want you to know, that in chlorination of cycloalkane compounds, in a chlorination means you are reacting chlorine molecules with what? With a compound per se. So when we are talking about chlorination of cyclo compounds, the means that we are reacting chlorine molecule with what? Cycloalkane compounds. So look at something like this. Okay, look at something. See something here. This is a cyclic compound. No matter the cyclic compound, okay, no matter the cyclic compounds, all the hydrogens that have been bonded to that specific carbon. Here there's a carbon, here there's a carbon, there's a carbon, there's a carbon, there's a carbon, making 5 carbons. Regardless of the number of what carbons to give you the cyclo compound, let's say cyclononane, cyclooctane, cyclodecane, and all those stuffs, all the hydrogens that have been bonded to it, they are all secondary hydrogens. And all these hydrogens are equivalent, because they are secondary. All these hydrogens are equivalent. For that matter, when you react, or when the cycloalkane compound undergo chlorination, it yields only one product. It will yield only one product. If it attacks this hydrogen, this hydrogen here is what? A secondary what? Hydrogen. If it attacks this hydrogen, it's a secondary hydrogen. If it attacks this hydrogen, it's a secondary hydrogen. So it's going to yield what? Only one product. For that matter, they say what? All hydrogens bonded to all the hydrogen bonded to the carbons are secondary hydrogens. Hence, only one compound will be what? Will be formed. Note, for alkanes with equivalent hydrogens, atoms For alkenes with what equivalent hydrogen atoms, only one product is what formed, or only one product is yielded, as I explained earlier. So I hope you understand what I was trying to mean by what. So in my next video, I'll be discussing about what the isomers. I'm going to go deep into what enantiomers and what diastereomers and all those stuff. So make sure you subscribe to the channel and like and comment. Anything that you don't understand, you can put it in the comment section. I'll make sure I'll do a video about it if there is a need. Thank you.
Baby, why you do me so? Girl, your body tonight. I go pop champagne for your body tonight.